mass. So what is gravitational lensing? Basically you have distant sources in the universe, so galaxies, distant galaxies, and you have mass concentrations, dark matter lumps basically, right? And they could be dark matter that's associated with an individual galaxy or with a cluster of galaxies, huge amounts of dark matter. And you know, all the webs that we saw, we are looking at galaxies that are behind us, that are further away from us, that are behind these webs. So this could be one of those webby things that we saw in that simulation. So what that actually does is light rays from this object are actually deflected, they're gravitationally focused. So you, instead of the actual position of the galaxy, you end up seeing it at a slightly different position. Okay, you think it's at a different position. And it turns out, like geometrical optics, and many of you might have done these experiments in school where you have a concave or a convex glass lens, a candle, you have a screen. Depending on the relative orientation of the screen and the light source, you can get sometimes an inverted image, you can get a magnified image, demagnified image. Same thing happens in the universe, except that in the universe, you don't have both concave and convex lenses. There's mass is positive. So it's the equivalent of saying you have only one kind of lens, you have only these focusing lenses. And so you end up, however, you end up doing something more phenomenal, because in the, if you have a very massive clump along the line of sight, you actually end up splitting the image of one object into 2 images, 3 images, 5 images. And that's all seen. Okay, so that is seen here. Can we get the lights in? I guess this is it, right? So what this is a cluster of galaxies. It's a very spectacular cluster. So what you end up seeing here as these very distorted, elongated arcs are actually elongated, distorted images of a rather regular looking elliptical-ish galaxy that just happens to be lying behind a very massive dark matter clump, which is sitting all over here. Okay, so what we can do, because we know the undistorted shapes of galaxies. Why do we know that? Because regions of the sky that have large mass concentrations are rare. If you notice, when going back into the simulations, there are more holes than there are webs. So these regions are rare. So when we look at the sky in general, we're looking statistically at undistorted shapes of galaxies. But when we look through a cluster, we're looking at a cylinder through the cluster. It's a special location because there's a huge amount of mass there, and you see distorted shapes. So since you have a prior distribution of undistorted shapes, you have distorted shapes, you can invert the problem and solve for all the mass in that cylinder. And that's what we do. Most of us who work on gravitational lensing, we are in a cylinder, but along spatially in slices, we are reconstructing the mass distribution that is required to produce the deflections that are seen. And the deflections are seen because of the elongations they produce. That's measurable with the Hubble Space Telescope. Actually, I'll try and show you. So anyway, this is what we do. So we've assumed no relationship between mass and light. So this is our reconstruction of the mass of this object. This region is here. Okay, it's the central part where you have the brightest galaxies. And what you see here is the distribution, detailed distribution of dark matter derived from the data. Okay, only thing I have assumed here, I have not assumed initial condition to little dog. So what people like me have been doing for the past few years, those of us who are uncomfortable about these relationships between mass and light, these ad hoc relationships, have been doing this kind of work. And what we can do, this is an inventory of dark matter clumps. So I can look at this cluster and I can say, okay, I can count the clumps, I know their masses. Their masses are basically proportional to the heights here. So I know how many clumps I have, and I can go into a simulation. I can pick a region that is as dense as this cluster, that has roughly the same mass within this range. I can count the clumps. Okay? And then I can pick different kinds of dark matter to initialize this model, count the clumps, and see if there's a difference in the clumps. And of course, you know, to do all of this is just an animation to show you how. So this is a background screen of galaxies, all of which are circular. But lensing dramatically distorts those shapes. And these are observed. So just to give you an example, I showed you this because this is an image, a ground-based image of an elongated galaxy. So that's a lensed galaxy. And that provides so you see something like that, right? So that you can reproduce that. We understand it extremely well. Okay, so you can count the clumps, and that's what's done here. It doesn't matter what the details of this plot are. The red histograms are clumps we've counted in various clusters of galaxies. The black histogram is from the Millennium simulations, where again you're counting dark matter clumps. So you're measuring dark matter clumps, you're counting dark matter clumps. And the correspondence is incredibly good. There's one case where the correspondence is not good at all, and that's a very special case. That's a case where you have two clusters that happen to be merging along the line of sight. Because we are seeing everything projected on the sky, we don't have that information. So it doesn't quite match. The Millennium simulation doesn't have a cluster that has the same dynamics as this real cluster. That's a very rare case. But it's a rare. And the question is, you may ask, okay, how powerful is this? Extremely powerful. Okay, it turns out, if I change the initial conditions, this is cold dark matter, only gravitation, warm dark matter, so that's neutrinos, added some portion of neutrinos. Notice how smooth the warm dark matter model is. It's extremely smooth compared to the cold dark matter, which is very clumpy. So looking at the dark matter, so the jargon word for this is substructure. You might have heard it. So looking at just the substructure distribution, we have ruled out this model. Okay, so it's an excellent correspondence with this model. And so I think this is the only observational test of this model that is independent of these ad hoc relationships between mass and light. Yeah?
Wait, you keep talking about the worry about the relationship between matter and light. Yeah. It seems like you could use your results to then test.
Yes, we have.
Because you're getting an independent distribution of dark matter, and then you can see what the light distribution is. So you should be able to nail it down that way.
Right, so what we have nailed down is that relationship in that particular environment of a cluster. It is not a universal relationship. Absolutely. We've played that game. And so we have a very good understanding now in the dense regions of the universe, like clusters, how mass and light should be related. But it's very clear that that same relationship doesn't work in less dense parts. So we know that. So we know that there is freedom there. Right? There's legitimately freedom there. Okay, so the question is, can cosmological simulations really help us validate theories? And it turns out that it can help us validate theories of the sort where there is a slight difference either in the assumed properties of the dark matter particle. So this tau CDM is the neutrino case that I just showed you. So you have neutrinos constitute some dark matter. And it hasn't come out very well, but it looks actually on the screen, you can see it quite nicely. There is a difference in the statistics of these fields. Okay, these are all time slices for different realizations of different initial conditions, properties for the dark matter, and taken at different instances of time. So this is today, that redshift 0 corresponds to today, and this corresponds to a slightly earlier time. This is when the universe is about 8 gigayears old, and the universe is about 10 gigayears old. So in fact, you can discriminate between these 4 models. It turns out they're the only 4 models we can actually simulate at the moment. Okay? That we have a power spectrum 4 that we can propagate forward in simulations. And it turns out that we can sort of discriminate between these 4. We can rule this one out. And the supernovae data have ruled this one out. So this is a realization where the matter content is not dominated by dark energy. There's no dark energy in this model. There's dark energy in this model. So it turns out that even the distribution of galaxies and clumps in the universe is in agreement with the existence of dark energy. Although the evidence for dark energy came from a completely different set of observations of supernovae. Right? So at the moment, we've been able to rule out classes of models. But I want to point out that, these models are not wildly different. In the sense that, they don't have as much intellectual diversity as you would philosophically like to say, something that is so radically different is ruled out. We don't have a framework, and as I said, I'm really stressing the fact that the way we've developed this framework, it's very, very hard to come up with an entirely new, valid framework with which to compare lambda CDM. So there's a way in which you can never, ever, ideally you want proof, you want validation, you want explanation, either full or partial, and you want a prediction. And it turns out that was my last slide, that essentially the